Good morning. This is Kumar, Assistant Professor, HNS Department from Regenerative Engineering College. The subject is Applied Physics. The first unit is Quantum Mechanics. The topic we are discussed today, Schrodinger time independent wave equation and the application of the Schrodinger time independent wave equation. Before we we explain Schrodinger time independent wave equation. And we explain the simple definition of the Heisenberg uncertainty principle. What is the statement of the Heisenberg uncertainty principle? The uncertainty principle states that the position and momentum of the particle cannot be determined simultaneously to any desired degree of accuracy. That is, at a time, momentum and position we cannot accurately determine. We cannot calculate it or we cannot determine at a time. Suppose we determine the position of the particle, we cannot determine the momentum. Nothing but what is the velocity and what is the momentum of the particles. Suppose the particle having some position, we determine accurately the what is the position of the particles. But we cannot define the or we cannot accurately determine the position, sorry, momentum of the particles. Suppose we determine the momentum or velocity of the particles, we cannot determine exactly what is the position of the particles. We particles. That is, we suppose we determine the positions, we cannot determine the momentum. Suppose we determine the momentum, we cannot determine the position. That is the statement of the Heisenberg uncertainty principles. What is the principle? The particle moving at the time, the particle having the position and the momentum. According to uncertainty principle, suppose we define the position of the particle, we cannot define the momentum. Suppose we define the momentum of the particle, we cannot determine the position of the particle. That is the definition of the Heisenberg uncertainty principle. The equation is del x dot del p equal greater than or equal to h by 4 pi. X is momentum, p is momentum. The product of momentum and position is equal or greater than h by 4 pi. H is Planck constant 4 pi. The product of momentum and position must be equal or greater than the position in the all equal greater than the h by 4. And also we determine the energy and time according to the uncertainty rules. Energy and the product of energy and time is greater than or equal to the h by 4 pi. Same as angular momentum and the angle. The product of the angular momentum and the theta angles. This is also the product of angular momentum angle is greater than or equal to the h by 4 pi. This is the simple definition of Heisenberg uncertainty principle. Next one is the Schrodinger time independent wave equations. According to the de Broglie theory, a particle of mass m is always associated with a wave whose wavelength is given by lambda equal to h by m. According to the de Broglie, the particle having mass m and moving with velocity v, at that time, the wavelength of the de Broglie wavelength of the particle is lambda equal to h by m. If particle has wave properties, it is expected that there should be some sort of wave equation which describe the behavior of the particles. Consider a system of stationary wave associated with the particles. You consider the system having a stationary wave associated with the particles. And that is then we consider, let us x, y, z be the coordinates of the particles. The particle having the coordinates x, y, z. And z is the wave displacement for the de Broglie wave at any time. At any time, the particle having the coordinates x, y, z and the displacement of the particle, that is the wave displacement of the particle is xi. The classical differential equation of the wave motion is given by dou square xi by dou t square equal to v t square into dou square xi by dou x square plus dou square xi by dou square plus dou square xi by dou z square. Then to write dou square xi by dou t square equal to v square del square xi. Nothing but here del is a D'Alembert principle. That is the equal is del square equal to dou square by dou x square, dou square by dou y square plus dou square by dou z square. Del square is being Laplace operator. V is the wave velocity. The solution of equation 1 give psi has a periodically displacement in terms of the time. Then we read the equation 1. The wave function of the has a periodically displacement in term of the time you write, that is psi x y z t equal to psi x y z e power I omega t. Right in the then where psi naught x y z is a function of x y z and gives the amplitude at the point. Consider the equation 2 can also expressed as equation 2 right in the wave function xyz in the amplitude right there. Psi into r bar t equal to psi naught r into e power I omega t. Differentiation equation 3 in twice. Equation 3, we get the differentiation in twice. Then we get dou square psi by dou t square equal to minus omega square psi naught r bar e power I omega t. And then we write equal to minus omega square psi. Substitute the value of dou square psi by dou t in equation 1. In equation 1, we substitute the value of the dou square psi by dou t square. Then v square del square xi equal to minus omega square xi. Then we cross multiplications dou square xi plus omega square by v square xi equal to 0. That is the equation 4. But omega equal to 2 pi mu. And then we write 2 pi equal to v by lambda. Omega by v equal to 2 pi by lambda. Then substitute the value of omega by v in equation 4. We have dou square xi plus 4 pi square lambda square xi equal to 0. Nothing but omega value equal to omega by v. Nothing but 2 pi v by lambda. That's we write the in this equation. Now from de Broglie relation, lambda equal to h by mu. Lambda value substitute in equation 5. Then what is the we get? We get the equation del square xi equal to 4 pi square h square m square v square xi equal to 0. That is the equation 6. If E and E are the total and the total energy and potential energy of the particles respectively. E is nothing but total energy. V is nothing but potential energy. Nothing but kinetic energy and potential energy of the particles with respectively. Then it is kinetic energy is half m square given by half m square equal to nothing but E minus V. The total energy E equal to kinetic energy plus potential energy. That is, then you write the kinetic energy. Kinetic energy equal to total energy E minus V square. Then we cross multiplications. In cross multiplication and m square V square equal to 2m E minus V. Cross multiply with the m on both sides. That's why m square v square 2m into a minus v. Use cross multiplication and multiply with the m. From equation 6 and 7, the equation 6 is del square xi plus 4 pi square h square m square v square xi equal to 0, and equation 7 is m square v square equal to 2m into e minus v. From equation 6 and 7, we have del square xi plus 4 pi square h square into em e minus v into xi equal to 0. Then del square xi equal to, so it is 4 into 2 into 8, 8 pi square m by h square e minus v into xi equal to 0. The equation 8 is known as Schrodinger time independent wave equation. This equation is called the Schrodinger time independent wave equation. And substitute the h cut is equal to h by 2 pi in equation 8. The Schrodinger wave equation can be written as del square xi plus 2m by h cut square e minus v xi equal to 0. Suppose for a free particle, potential V equal to potential energy equal to 0. And the Schrodinger wave equation for free particle can be expressed as del square xi equal to 2m t h cut square into xi equal to 0. That is the Schrodinger time independent wave equation. This is the Schrodinger time independent wave equations. Suppose the particle is free particle, that is the kinetic energy, the supportation energy is 0. At that time, the free particle of the Schrodinger equation is in this. Then the next one is physical application of the wave functions. What is the physical application of the wave functions? The wave functions has no direct physical meaning. If it is a complex quantity, representative the variation of the matter. It cannot the particle nature and it associated with nature statistically. Wave function give the information about particle behavior. Wave function give the information about the particle behavior. What is the behavior of the particle? That information give the wave functions. We can share that the wave function has probability amplitude since it is used to find the location of the particles. What is the, we can say that wave function, the probability amplitude. Wave function has the probability and sensitivity and it is used to find the location of the particles. What is the location of the particle? Find out the wave function of the with the probability amplitude. Xi star or mod xi square is the probability density function. That is called the xi star or mod xi square is called the probability density functions. Xi star dx dy z give the probability of finding the electron in the region of the space between x and y and x plus dx and y plus dy and z plus dy. If the particle is represent integral mod xi square dx dy dz equal to 1. The probability density function of the xi star or mod xi square is called the probability density. The probability density in the coordinates x, y, z, you write that equation is triple integral mod xi square dx dy dz equal to 1. That is called the normalization equations. That is normalization. Suppose the normalization equation is triple integral mod xi square dx dy z equal to 1. That's called the normalization equation. Next, Born interpretation of the wave functions. Max Born in 1926 formulated that the square amplitude of the wave function xi at any given point is proportional to the probability of finding the particle at that point. What is the Max Born? What is the formula? Square amplitude the wave functions. Square amplitude of the wave function is directly proportional to the probability of finding the particle at that point. Where which point we find the probability that is exactly proportional to the square function of the wave function. Nothing but z star or mod z square is directly proportional to the probability of the particles. At any point, what is the probability of the particle? That is exactly proportional to the mod z square. Nothing but both are equal. Square modulus of the wave function is exactly equal to the probability of the that particle. That's why both are directly proportional. Probability density is given by Px is directly proportional to mod x xi x comma t whole square equal to xi x comma t xi star x comma t. Since the probability of finding the particle in equation 14 is selected region of the space A unity. So the above expression can be given as if r comma t dz equal to integral mod xi r comma t whole square dz equal to 1. Xi satisfy above required is said to be normalizations. One is nothing but normalization. The wave function psi must be single value, finite and continuous everywhere. The wave function be must be having the single value, finite and continue everywhere. Next, that is the Bohr interpretations and the what is the physical signification of the wave functions. Depending on the physical signification of the wave function and the Bohr interpretations from both this from both information, we explained to the application of the Schrodinger wave equation. Both information is considered in the Schrodinger applications. They are used in the why at the application of the Schrodinger equation, we find out the probability density. And then the probability density is nothing but wave function, proportional to the wave function. That's why both information used in the application of the Schrodinger wave equations. Sorry, that is placed. Next, when the Schrodinger time independent wave equations and the topics of the Born interpretation and physical signification of the wave functions. Then the next topic is application of the Schrodinger time independent wave equations. The one application is particle in one dimensional box. The particle take in one dimensional box. That is the application of the Schrodinger wave equation. Consider a particle moving inside a box along to the x direction. We consider a particle moving inside the box along to the x-axis. Suppose we consider the box, the particle moving along to the x-axis. The particle is bouncing back and forth between the walls of the box. This is the box, the particle moving along to the x-axis, and the particle is bouncing on the wall and the particle moving back and forth. The box has potential barrier at x equal to 0 and x equal to L. This is suppose this is the particle at the this is the box. This is the one end of the box. This is the another end of the box. Nothing but here one end is at the x equal to 0, another one is x equal to L. The potential, the particle having the potential at x equal to 0, the potential how much at x is equal to 0 is equal to infinity, and x is equal to L, the potential is infinity. Nothing but at the two side of the box or end of the box, the particle is incident bones, nothing but falling on the wall, and the particle is back come on back. Why here the potential energy is infinity. Nothing but what is the particle having the walls. The particle cannot escape from the walls. We consider the wall in the here, the potential energy is infinity. When the potential energy is infinity, the particle cannot go to the outside. The particle only having the inside of the box. The particle moving with the some velocity. Then nothing the particle having the kinetic energy. That is, the box is supposed to have a at x is equal to 0 and x is equal to L. The particle has mass m and it is position x at any instant is given by x equal to less than x less than L. Then the particle energy V of the potential energy V of the particle is infinite on the both sides of the wall. The potential energy V of the particle can be assumed to be 0 between x is equal to 0 and x is equal to L. Between the x is equal to 0 and x is equal to L, between the here, in this side, the potential energy is 0. But at the exactly x is equal to 0, x is equal to L, the potential energy is infinity. When the potential energy is infinity, the particle cannot escape from the box. The particle cannot moving from outside. Why? The potential energy is infinity. And inside of the box, the particle having only the kinetic energy. The potential energy inside of the box is 0. In terms of the boundary conditions, impressed by the problem, the potential function is, suppose we take the potential functions. We take the different potential functions. Consider on the box. V equal to 0 for x 0 less than x less than L. The x value greater than 0 less than L. Nothing but the potential energy is V equal to 0 inside. The x value greater than 0 less than L. Nothing but inside of the box, the potential energy is 0. Only kinetic energy. Another. V equal to infinity for x equal to r less than 0. The x value here, the potential energy is infinity. And where the x value is equal to 0 or less than 0. And the potential energy is infinity. And another, the potential energy is infinity for x value greater equal to or greater than L. Greater than L, sorry, equal to L or x value greater than L. In this side, the potential energy is infinity. And the x value equal to 0 or less than 0, potential energy is 0, sorry, potential energy is infinity, and x is equal to L or greater than L, the potential energy is infinity. Three are the boundary conditions of the potential. If the particle cannot exist outside the box, why? Here the particle potential energy is infinity. Here the particle potential energy is infinity. That's why the particle cannot exit outside the box. The particle cannot exit outside the box. The particle only moving in the inside of the box. Why here the potential energy infinity? Where the potential energy infinity, the particle cannot escape from the outside. Outside of the box. And so its wave function is a 0 for x equal to or less than 0 and x equal or greater than L. The wave function is 0 where x is equal to 0 or less than 0. or x equal to L or greater than L. Here, wave function is 0. Here, wave function is 0. Here, no form of the wave functions. The Schrodinger equation become, then we write the, what is the, now write the Schrodinger equation. What is the Schrodinger equation? Dou square xi by dou h square plus 8 pi square m by h square e xi equal to 0. This is the Schrodinger wave equations. Here, we put 8 pi square me by h square equal to k square. What is the simply this part, this part. What is the 8 pi square m e by h square equal to, we consider the k square, and the equation become, now the equation of how to d square z by dx square plus k square z equal to 0. Simply here we substitute the k square. The general solution of the equation 2 is, what is the general equation? Write the equation 2 having the general equation is z equal to a sin kx plus b cos kx. That is the general solution of the equation 2. No, the boundary condition can be used to evaluate the constant a and b in equation 3. From we evaluate the constant a by a and b, we apply the boundary conditions. What is the first boundary condition? At z equal to 0, at x equal to 0. Wave function is 0 at x equal to 0. Then equation 3 is only, suppose we substitute the x value equal to here, this part is 0 and z equal to 0 here. Only we are having the x equal to 0, cos 0 equal to 1, nothing but we have only the b. Nothing but b equal to 0, b equal to 0. Substitute b value in equation 3. In equation 3, b value substitute. That is z of x equal to a sin kx. A sin kx. The b value substitute in equation 3, we get the equation 4. And another one is z equal to 0 at x equal to L. The x wave function is, a wave function is 0 at x equal to 0 at x equal to L. Inside of the box is wave function is 0. Then equation 4, a sin kl equal to 0, z equal to 0, but a cannot 0, nothing but a is constant. That's why no, that cannot is equal to the 0. Then we write the sin kl equal to 0, kl equal to n pi, where n is an integer. Then we write k equal to n pi by l. That is the equation 5. Substitute equation 5 in equation 4. Then we get z of x equal to a sin n pi by l into x. That is the equation 6. The energy of the particle from equation 1a and 5, that is a n square pi square by l square, and that is equal 8 pi square me by h square. The energy of the particle from equation 1a and 5. From equation 5 in this and 1a. This is the 1a. From those equation, we get that in this box. N square pi square by L square equal to 8 pi square m e by h square. That is En equal to n square h square 8 m L square. That is the energy level. That is the energy values of the waves. Yes, integer n you write n equal to 1, 2, 3, and so on. For each value of n, this is an energy level. Remember, the equation of the energy level is En equal to n square h square by 8 m L square. Suppose integer value n equal to substitute 1, 2, 3, so on. Here suppose we substitute the n equal to 1, that is the energy level is h square by 8 m L square. Suppose we write the n equal to 2, we substitute the n equal to 2. What is the 4? 4 h square 8 m L square. The energy value is What is the at the energy level n equal to the energy value is 4 h square 8 m by mx. Suppose the n value substitute 3 n, that is the n substitute 3, nothing but 3 whole square. That is n equal to 9 h square 8 m by l square. That is why we substitute the n value in energy level equation is the En equal to n square h square by 8m l square. We n value substitute 1, 2, 3 and so on. You write the equation. Each value of En is called the energy value. Each value of En is called the energy value and corresponding wave function is called the wave function is called the wave functions. The each value called the energy value and corresponding wave function is called the wave function. N is called the wave function. Thus, inside the box, the particle can only having the discrete energy value. Specified by equation 7. Note that the particle cannot have zero energy. The discrete values, nothing but the particle, the inside the box of the particle having only the discrete energy. Discrete energy nothing but the different state having the same energy values. Different state having the same energy is called the discrete energy. The value of A in equation 6 can be obtained by applying normalization condition. Since the particle is inside the box of the length L, the probability that the particle is found inside the box is unity. That's why you write the limits 0 to L integral z star z dx equal to 1 according to the normalization condition. And we write the substitute the values of the z star here. What is the z star value normalization? A square integral of 0 to L sin square n pi x by L into dx equal to 1. We take in the common a square by 2 integral 0 to 1 minus cos 2 nx by L dx equal to 1. Sin square nothing but 1 minus cos square by t formula. Sin square equal to sin square x equal to 1 minus cos 2x by 2. Here 2 taken common and write that this equation in the form 1 minus cos 2x. 1 minus cos 2x nothing but nx by L. You write in the formula. Then we taken a square by 2 0 integral. We apply the integral here and here different. Then integral 0 to L dx minus integral to 0 to L cos 2x nx by L dx equal to 1. Then we applied limits. A square by 2 equal to 0 to limits dx equal to x and minus the integration of this part is sin 2 nx x by L by 2 nx by L limit 0 to L equal to 1. This part is considered only the we consider is equal to this value is simplified, we get the 0. This value is simplified, we get the 0. The remaining is a square by 2 into x. And we applied the limit 0 to L. Then we get a square by 2 equal to L into 1. Then we add the cross multiplications. A equal to L by 2 and a square a square L by 2, then a equal to under root of 2 by L. Cross multiplication to here then numerator to denominator L. A square equal to 2 by L, nothing but a equal to under root of 2 by L. That is the equation 8. The normalized wave function of the particle Is the normalized wave function of the particles in equation is under root of 2 by L sin nx by L. That is the equation 9. So you write the wave functions. Here, wave function 1, nothing but substitute the equation. Here, wave function is like this. We apply the n equal to 2. The wave function is like we apply the n equal to 2. Wave function is like this. And we write the wave function and probability density of the particle in one dimension is like this. In the probability density or in the probability z star or mod z square, we write the wave function is like this. This is the 1, this is the 2, this is the 3. The wave function probability density of the particle in a one dimension is in this levels. The normalized wave function z1, z2, z3 and the corresponding probability function z star are the plotted in the figure. This is the wave normalized wave function. This is the normalized wave function. First n equal to 1, wave function 1, 2, 3. And the corresponding probability function is like this. This is the normalized wave function z1, z2, z3. Wave function is like this. And the corresponding probability function is mod z square is 1, 2, 3 is like this. This is the application of the Schrodinger wave equation, the particle in a one-dimensional equations. First one is the Schrodinger time independent wave equations. Then application of the physical application of the wave function. Then bond interpretation. Then afterward the application of the Schrodinger time independent wave equation particle in a one-dimension box. This is the today topics. Okay, thank you.